So when the assembler actually takes the code that you write and converts it into machine code, it is assembling your assembly language into a 32-bit number that is stored in memory. This little chunk of description is how that actually works, because I'm going to want you to be able to do this by hand, because if you can do it by hand, you can really understand how it works. If we look at the simulator one more time, we can see that, again, when we asked it to do, for example, load immediate V0 and 4, it doesn't actually do load immediate V0, 4. It does or immediate V0, 4. And that or immediate V0, 4 gets stored in memory as this 32-bit number, 34020004. And the question is, how do we get from or I this to that? Or how can you look at this instruction and know that this is actually or immediate? How can you look at this 0000000C and know that that is a request for a system call? Well, this is the encodings that we're talking about. And most of the magical sheet that I gave you actually corresponds to these encodings. So load upper immediate, as an example, if I wanted to put 4097 into the upper immediate register, the upper immediate half of the assembler temporary register, this is the code, 3C011001. And you might already guess that this 1001 is that immediate number. Well, let's look at how this actually works. This is going to be done using our special sheet, which I showed you. And again, this is what the sheet looks like. There's an awful lot of detail on this sheet, but the more you work with it, the more you will understand how it works. So the sheet, first of all, on this side here, has all of the possible instructions for every possible instruction in MIPS, right? That's it. That's all the instructions you have to learn. Down here are the 5, if you count the floating point numbers, formats for the instructions. They can be either register format, immediate format, or jump format, which you already learned when we walked through the construction of this machine. Up here are a bunch of notes around each kind of instruction and how they're organized. These are different branch instructions. These are floating point instructions. Don't worry about that stuff in the middle quite yet. Here is the complete register file, complete with every register and its name. And so we can make a connection between, if I say store some information in V0, I can look up here what register V0 actually is. Over here are some common pseudo instructions. Then we have some assembler directives, and then we have service calls, and we have the hex value. This is a slightly older version. The version that's on the website is a little bit different, but basically the information is the same. So be aware of how this sheet works and how to make sure that you get the most out of it. To do an encoding, what you're going to do is you're going to take the instruction itself and you're going to look up on the sheet what the instruction corresponds to and then write out the 32-bit numbers that are there. So for example, to look at unsigned subtract as an example, we're going to look up this instruction here. We're going to find that it's an Rtype, AL03 category, and then the bits that correspond to the value of the opcode and the function code. And then we're going to use the category to look up some additional information about it there. We're going to use the format to figure out what the individual bits of the 32-bit number correspond to. And then we're going to take the function code and the opcode and put them in their appropriate places in that format, and then fill in the registers, and then we're done. So this is sort of the general format for this. I'm going to walk through a specific example in a minute. This says we're going to take the value of the registers and put them in the right places. Okay, the important thing to remember is that not everything is on this sheet, but you should get used to writing code with it, right? So emphasize, right? So let's do an example. These are the examples that are in the form here. We're going to do an example, and then hopefully that'll give you an idea of how to do this. So the example we're going to do is going to be, I've lost it. Where did it go? We're going to do add into register T1 the values that are in register V0 and the value that's in register A0. So this is the instruction that we want to know the 32-bit number for. And all of this information is on our sheet. So First of all, we look on our sheet and we say add. Well, add is our format. Our format is opcode, rs, rt, rd, shift amount, and function. So we'll look at opcode, and then rs, and then rt, and then rd, and then shift amount, and then function. Those are the 6 fields that we have to find the values of to figure out this instruction. So we'll look back at the top and look at add. The opcode is here. It's all zeros. A lot of opcodes is all zeros. We'll talk about that in a second. And the funct code is 1, 0, 0, 0, 0, 0. So opcode is 6 zeros, 0, 0, 0, 0, 0, 0. And the function code is 1, 0, 0, 0, 0, 0. Now, ALU type instructions are special in that the opcode is always 0. If we look at this, the opcode is 0 for all the R-type instructions. Almost all R-type instructions, oh, I didn't see it there. Almost all R-type instructions have an opcode that's 0, and the function code extends that opcode. And we talked about this again when we built the hardware, but this is how you do this in MIPS. Okay, so the opcode is 0, 6 bits. Now we need RS, RT, and RD. Well, if we look here, RS, RT, and RD, those are the values we're going to fill in. But what are they? Well, let's look at the category information for ALU R-type instructions. It gives you an example, a assembly language example. Add RD, RT, and RS, and it says the registered RD gets RS plus RT. So RD is the first one, so this is going to be RD. And then RS is the second one, RS. And then RT is a third one, RT. So unfortunately, they're in a different order in the instruction as they are in the assembly language, but this kind of complexity is what's going to happen. It's unfortunate. So RS is the first one. RS is V0. What is V0? We'll look at the register file, and we'll look through the register file and look for V0. V0 is register 2. Okay, so we'll put in the number 2. Now, all of these registers are 5-bit specifications because there's 32 registers in the register file. So to pick one of 32, you need 5 bits. So to specify the number 2 in 5 bits, it's 0, 0, 0, 1, 0. That's 2. Then what? RT is A0. What's register A0? Register A0 is register 4. So 1, 2, 4. 1, 2, 4. 8, 16. And then register D is T1. Well, we'll look at T1 here. T1, we see T0 here is 8. So T1 must be 9. It's right beside it. So register 9 is this. 9. What do we do with the shift amount? Well, the shift amount is going to be used mostly for shift instructions. And anything that's not a shift instruction, we'll just ignore the shift amount. It's an unused field. And we're going to leave it as zeros. Okay, so that's 32 bits. Those are the 32 bits that correspond to that instruction. And these 3 registers are going to go to the register file. Where's my computer? Here's my computer, right? Are going to address the register file and tell us which instructions, which registers we're interested in. The opcode and the function code are going to go to the rest of the hardware and specify what to do with the rest of the machine. Data memory is ignored. This multiplexer chooses 0. This multiplexer chooses 0. This multiplexer chooses 1, etc., etc. All those specifications for the individual control bits are indicated by opcode and function code. Now that's the 32-bit numbers, but to finish this problem, we want to actually see what it looks like in hex. So we're going to take this 32-bit number, we're going to split it up into 4-bit chunks, and each 4-bit chunk is 1 hex bit. So there's 4 bits here, 4 bits here, 4 bits here, 4 bits there, 4 bits, 4 bits, 4 bits, and 4 bits. And if you can't remember, on the sheet is the hex bits. Right? So remember, hexadecimal is a 16 symbol number system, right? Our regular base 10 is a 10 symbol number system, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. To make a 15 symbol number system, 16, 16 symbol number system, we go from 0 to 9, and then we can't use the number 10 because that has two symbols, a 1 and a 0. So instead of 10, we use A, and then B, C, D, E, F. 0 for 0, F for 15, and this is what's going to give us our hexadecimal code for that 32-bit number. This is 0, this is 0, this is 1, 2, 4, this is 4, this is 4, this is 8, this is 2, and this is 0. We put a 0x in front of it to indicate its hex, and if we see this in code somewhere, we know that that corresponds to this instruction. And that's it. That's all there is to it. Let's do another one. Let's do the OR immediate like we saw in our example. My printer's going. The OR immediate that we saw in the example was OR immediate, and then V0, and then I believe it was the value of AT, and then the value, oh no, we'll do this one. We'll do OR immediate into V0, register 0, and then, I'll write this out again. OR immediate, V0, 0, 4. There's an instruction that was the result of a pseudo instruction. The pseudo instruction was load immediate 4. That translates into OR immediate into V0 with the register called 0 and 4. Well, let's look at what that means for a second. There are a number of special registers that we saw already. Register 0 is a special register that just has the value of 0. We're going to use it so often that it's going to be useful to do that. So, OR immediate, let's look at the sheet. We look through here, bitwise OR immediate. This is an I format instruction. Let's look at I format. I format instruction has an opcode, RS, RT, and then the immediate value. So this is an I format, which has an opcode, RS, RT, and then immediate value. Opcode for OR immediate, bitwise OR immediate is 001101. 001101. RS, well, RS is there and RT is there. How do we know that? Well, RS, RT, but if you look at the immediate style ALU instructions, it's going to be add immediate into RT, the value for RS, as an example. So RT is our destination register. It's listed first, then RS. And so we list RT first. RT is V0, but in the instruction, we list RS first, which is the 0 register. What's the address of the 0 register? 0. What's the address of V0? V0 is register 2. And then the immediate value is a 32-bit number corresponding to the number that you want to OR with 0 and put in V0, which is 4. What's 4 in binary? Well, it's 0, it's 100, but we need 32 bits. So it's 0000000000000100. That's the number 4 in 32 bits. Now we split it up into groups of 4. And we get 3, 4, 0, 2, 0004. And this makes sense because that 0004 is the immediate value that we're going to be ORing with register V0. That's hex 0x34020004. And if we look at our code here, 34020004, that's why that corresponds to this instruction. So that's your encodings. The other direction is going to be decoding, which just does the other thing, opposite direction. If I take a hex value, let's do a quick decode just to confirm with this. 3C00, so the last direction, 0x3C011001. So what is this instruction? Well, to do it the other direction, what we're going to do first is we're going to write this out into 32 bits, And then we're going to break it up into fields. So 3 is 0, 0, 1, 1. C is 1, 1, 0, 0. Then 0 is 0, 0, 0, 0, 0, 0, 0, 1. And then 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. That's the 32 bits that corresponds to 3C011001. Now we'll break it up into fields. The first field, see the problem with breaking up into fields is we don't know what format it's in. And we can't know until we figure out what the opcode is. So first we take the first 6 bits and we say 001111, and we just look down this opcode list and say, what is 001111? Well, it's right around, where is it? 001111, right? 3C1100. It's going to end up being that. So let's look. There it is right there. 001111 is load upper immediate. So now we know this is load upper immediate. We know it's an immediate format. That means that we can take 5 bits, and then 16 bits. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then these. And that should already look familiar because this is the example used at the beginning. This is 4097. And if you do the math, you can figure that out. That's just immediate value. This is register 0, and this is register 1. And register 1 is register assembler temporary. That's on our register file. Register 0 is assembler temporary. And for load upper immediate, we actually ignore, this. And so we have load upper immediate into assembler temporary, the value 4097. And if we look at our code, that is in fact what that instruction corresponds to. So now you have an idea of how to translate back and forth between instructions and the machine code that they correspond to.